Okay, so at this point you should have uh, attempted all of the rotational concept review. I would like to hear, just one second. I'd like to go through the answers. So let's start with number one. I want to make sure that we've got a good sense. Why is it off the screen? There, now you should be able to see it all. Okay, so I want to make sure we have a good sense of what these things. So if you have a number of revolutions, remember number of revolutions can easily become theta. But what you got to do is you got to multiply by 2 pi to get it into theta. Again, that conversion is on there. If you're given a rate of rotation in RPM, you've got to multiply by your 0.1047, and then you've got now omega in radians per second. Radians per second squared, there's no conversion you have to do. That's just alpha, right? The linear velocity of a point on the outside of the wheel. So what do I mean by that? I mean like, you know, I've done the thing with the bicycle wheel, right? And I've got that blue piece of tape on the side of the bicycle wheel. And if I wanted to know how fast is that blue piece of tape going, that would be linear velocity. And linear velocity or translational velocity is just plain v. E I want to talk about. So distance the wheel travels over a certain number of radians. That's L, right? Lowercase l, not to be confused with big L, right? So from the equation, L equals r theta. So that's what the distance that the wheel travels in a certain number of radians is. I just wanted to show you real quick this, if I can pull up here, this animation, because I think that this animation is helpful if you're having trouble, visualizing why this is the case, right? So here we've got a wheel, and as the wheel turns, you can see here, right, as the wheel turns, this arc length here, oh, now it's going on. Let's stop that. So this arc length is the amount of theta that's been traveling. I think that theta comes up actually. Oops. What did I just do? Anyway, so theta, right, is this arc length that's been traveled, and that's the same as, and then the arc length L, this thing's calling it S, but the arc length L is the same length that the object has traveled, right? So going back to the question then, the distance the wheel travels over a certain number of radians is going to be this L that you can find using L equals r theta, right? The speed of this wheel, right, if I want to know the speed that this wheel is traveling, it's v. That would be the linear velocity of a point on the outside of the wheel. But the linear velocity of a point outside the wheel is v. The distance the wheel travels over a certain number of radians is going to be its arc length that it travels, and it's going to be L. Moment of inertia we know is iota. Angular momentum is capital L, and torque is the Greek letter tau. Make sure you can get to that there. All right. So that's what we've got there. So that's question number one. Question number two talks about the skater, and specifically, let me see here. Do I have what the question was here? So it says, what would happen if a figure skater doing a pirouette will pull in her arms? Well, I got a video here to show you related to that, because when she's pulling in her arms here, right? What you should see. Oops. Well, I just lost my spot. When she pulls in her arms, let me get back to the beginning here. All right, it'll start here in a second. So right now, when her, sorry, can you see what's happening? I don't know if you can see what's happening. Just a second. There we go. All right. Here we go. Okay, so right now when her legs are out and her arms are out, right? If you think about the moment of inertia, iota equals mr squared, right? The r at this point is pretty large because she's got some mass out here at a far radius. So she's got a rather large iota, which is moment of inertia, which is resistance to spinning. So she's got a lot of resistance to spinning, which means she's traveling relatively slowly. But if she brings her arms in, right, and here in a minute she's going to bring her arms in really closely. As she brings her arms in, just one moment, There we go. She starts to go faster and faster and faster. Again, because now the iota, or the mass is at a shorter radius, the iota, that is moment of inertia, goes down. If the moment of inertia goes down, she wants to maintain her angular momentum. So she wants to maintain her L. If she wants to maintain her L, but her iota goes down, then her omega has to go up. So if we go back to the question, right, why is it that the skater, what happens when the skater brings in her arms is her iota is decreasing, and so she's going to start spinning faster and faster because her W is increasing. All right, so that's the skater. Question number 3 asks, why is it better? Why is it easier? Why can you put more force on a nut with a wrench as opposed to just sort of finger tightening it, right? And you can see here, right, if you're finger tightening it, what's your lever arm? Your radius. Your lever arm is just this distance, right? We can get more torque, because we know torque is lever arm times force, or torque is, this is using a different notation than we do, but it's the force times the radius. We call it radius times force perpendicular, but this is a torque, right? If I'm at a bigger radius, right, my torque increases, so I can have more torque at a wrench because my force is acting at a larger lever arm. So that's the one about the wrench. Number 4 asks, why is it that a disc has a lower moment of inertia than a hoop? And you could look at the equation, right, and you could say, well, the disc has 1/2 mr squared, the hoop is mr squared, so the hoop has a larger, it doesn't have the 1/2 in front of it, it's clearly larger. But why? And what I'm attempting to show in this slide is what's happening, right, is if you've got a hoop, all of your mass is out here at the maximum radius, right? If all of the mass is at the maximum radius, then it's, oops, I went ahead too fast. If all the mass is at the maximum radius, then it's going to be harder to rotate that because, again, all your mass is pushed out to the inside. What I'm attempting to show here with a disc is that if you have a disc, right, that mass gets to be spread out more. And so not all of the mass is out here at its maximum radius. Some of the mass is closer to the middle. And so a disc then ends up having a smaller moment of inertia than a hoop does because its mass is more spread out, closer to the center. Okay, question number 5. It gave you a list of things and it says, which is going to hit the ground first? Well, remember, having the diameter of the hoops and the discs are irrelevant because the only thing that affects how quickly an object rolls down the ramp, remember we did this on Wednesday or Thursday, we said that the only thing that affected how fast the object went down the ramp was not its mass, not its radius, only its geometry, right? And so what I've done is I've put those 4 objects you were given, I've put their moment of inertias here, right? And you can see the thing with the lowest moment of inertia is going to be the thing that wants to get up to speed the fastest. So the first thing down the ramp, the first thing that's going to hit the bottom of the ramp is the solid sphere because it's got the lowest moment of inertia. Again, it doesn't matter that it's it doesn't matter that it's 7 centimeters and these other things, some of them are 5 centimeters. That doesn't matter because the only thing that affects what hits first is the geometry. Okay, so the solid sphere hits first. The disk having an iota of 1/2, which is bigger than 2/5, hits second. And then these two are both mr squared. So there's going to be a tie between both hoops because, again, the diameter doesn't matter. Oops. Okay, question number 6. It talks about the carousel. And it says we've got 2 kids. We've got one towards the center of the carousel and one towards the outside of the carousel. And what I want to do is I want to show you here another YouTube clip. I don't need the sound. Speed. Forget the sound. But I like this clip because you imagine this is the one kid close to the center, right? And this is the other kid closer to the outside. And you can see that the kid closer to the outside, right, is moving faster. But which thing is moving faster? It's the velocity, the regular v that's moving faster when you're farther out, right? So the kid on the outside, which is, who is it? The kid on the outside, which was Bobby, right? Bobby's going to have a larger v, right? Bobby's going to have a larger v because he's moving faster here on the outside. Janie and Bobby, though, are both going to have the same omega, right? Because they complete a rotation in the same amount of time. So they have the same omega, but the person on the outside is going to have a larger velocity. Okay, so that's question number 6. Question number 7 about the bicycle wheel. We did this demo. I had some of you try it out on Friday where we got a bicycle wheel turning, right? And then you stood on a stationary carousel, or sorry, a stationary turntable. This drawing is showing someone standing on a stationary swivel chair. And we said, what happens if you have an angular momentum pointing up? So an L naught pointing up. Now again, you got to think about which way does this mean that the bicycle wheel is turning. And you do the right hand rule, right? You make your fingers curl in the direction of the spin, and then your thumb points in the direction of the L naught. So in this case, the thing's going to be spinning this way, right? Because as you follow it with your finger, your L naught has to be pointing up. Okay. So what happens if I flip it around? So if I flip it, obviously I'm going to have a negative L naught. I'm going to be pointing down, right? So what is going to be the angular momentum though of the swivel chair, right? And we got to look at the fact that angular momentum is conserved. So the angular momentum before this happens has to be the same as the angular momentum after this happens. Well, before this happens, right, what do I have? The only thing that has angular momentum is the wheel, right, which I'm calling angular momentum L naught. The chair has no angular momentum. So this is what I have before. Afterwards, I'm going to have two things moving. I'm going to have the chair or the turntable moving, and I'm going to have the wheel moving, which this time is moving at negative L naught. Let me move this thing down. So the chair is moving at negative L naught. And so if you solve this algebraically, you should see that the chair is now going to end up with an angular momentum twice the angular momentum of the wheel. Right? Because if you sort of add this L naught over here, you get that the L of the chair is 2 times L naught. So the chair is going to start rotating counterclockwise with an upward angular momentum with twice the momentum of the bicycle wheel. Does this mean it's going twice as fast? Not necessarily. It just means it's got twice the angular momentum. Okay, with any remaining time that you have left, you can work on your syllabus. Again, I'll be here tomorrow to answer your questions. We will also have a review tomorrow, and you've got a test coming up on Wednesday or Thursday, depending on what period you have. Have a good day, and I will see you tomorrow.